semester we were given the task of creating a soccer-playing robot for the RoboCup Small Size League. The RoboCup Small Size League is a part of a RoboCup Research Federation focused on subsystem coordination. A standard match usually consists of 16 teams competing 8 vs 8 and 6 vs 6 in Division B. The original mission of the RoboCup Challenge was to field a team of robots capable of winning against the Human Soccer World Cup champions by 2050. The robot will consist of 4 different subsystems: Vision, Kicker Dribbler, and Driver and AI. All subsystems will be compiled and controlled by a Raspberry Pi 3. The robot's diameter is exactly 170 mm. The robot contains 2 main subsystems that are responsible for moving the ball. The dribbler was designed using a pulley system to allow the ball to have enough backspin for the robot to traverse the field while keeping possession. The purple components represent the 3D printed parts. The motor, which is housed on top of the tumbler, is attached to a small pulley, whereas the tumbler is attached to a large pulley. Through this, using a rubber band belt, there will be more torque supplied to the tumbler. This will allow for the robot to spin the ball backwards along the rough surface. The kicker system is designed to kick the ball towards a goal. The design of the kicker is simply with a rack and pinion using a high torque motor. Attached to the rack are a set of springs. The torque motor will spin the gear represented in black. The teeth will push the rack backwards, tensioning the springs. Once the teeth on the gear have been exceeded, the kicker will launch.
The Vision subsystem utilized the Raspberry Pi Camera V2 with no external lenses. The code consists of multiple functions which threshold the different colors needed to be detected on the screen. For example, to detect the orange ball, the camera's color scale was initially converted from BGR to HSV. It was then given the thresholding color, in this case red and light orange, and then masked to turn everything that is within the threshold white and everything else black. An example of this will be seen shortly. Following the masking phase, the contours that were then created for the objects within the threshold. Once this was done, another function would be called to determine the biggest contour and draw a rectangle around it. The function would then also use the focal length equation to determine the distance and bearing of the object from the robot. The biggest limitation of the code would be its thresholding ability. When thresholding some of the objects on the field, the thresholding limits would sometimes clash with each other, causing it to detect over each other. This was an easy fix, but was also an ongoing issue.
When designing the navigation and AI system for the robot, it was important to consider the unique environment of the soccer field and obstacles that the robot needs to maneuver around. A reactive and localized navigation system was then chosen to meet the dynamic environment requirements that the robot would experience. To do this, a potential fields approach was implemented into the navigation software that scales the environment around the robot based on the detected bearings and range of the desired and undesirable objects on the field. This was then implemented into the navigation code and tested in VREP to determine the limitations and any errors that might occur. This navigational method was then combined with a state machine that breaks down the task that the robot needs to perform to successfully score a goal. This state machine model ensures a reactive system that will change states depending on the field layout and its dynamics.
The differential drive system was used with 2 gear motors with a gear ratio of 100:1. These gear motors met the specifications required for the calculated parameters of the friction and acceleration torque and high and low motor speeds. Both wheels were laser cut with a 60 mm diameter in size. Its teeth-like structure gave a more robust approach in driving and assisted in meeting the lower end of its speed of 0.05 meters per second. Motor controller modules were used to control 2 drive motors, the dribbler motor and the kicker motor. These modules utilize a IRF520 power MOSFETs, which would turn on using a PWM from the Raspberry Pi. The team managed to be under budget by $30 and completed the objective by the due date. Each team member responsible for their subsystem met their objective. From Team 19, thank you for watching.